Hi everyone, today I want to discuss the topic of hand gesture recognition in computer vision within our research called Investigating Hand Gesture Recognition Models 2D CNNs versus Visual Transformers. Today's agenda. Hand gesture recognition is vital in technologies like virtual and augmented reality, where gestures are key to human-computer interactions. Having accurate and fast hand gesture recognition is important for many reasons, including making it easier for people to communicate, especially those with disabilities. However, there are many challenges we face, such as different hand positions, changing illumination, and background noise. These challenges can make it difficult for our recognition system to work well. Today, our research aims to advance hand gesture recognition with following objectives: analyze modern approaches to hand gesture recognition, focusing on 2D convolutional neural networks and visual transformers, and evaluate the accuracy of hand gesture recognition models built on these architectures using datasets such as American Sign Language dataset and National University of Singapore dataset. Investigate the comparative effectiveness of the models using these architectures, considering factors like computational resources. Through these objectives, we aim to contribute valuable insights and advancements in the hand gesture recognition technologies with practical implications for real-world applications. In, uh, in the early stages of hand gesture recognition in computer vision, classical methods relied on manual feature extraction techniques such as color histograms, contours, uh, texture characteristics. While effective for specific tasks, these methods struggle to adapt to changing conditions like illumination variations and perspective changes. The introduction of deep learning improved accuracy in dynamic hand gestures and action recognition, although challenges remain in real-time systems. Innovative approaches such as CNN-SPP and eDenseNet have enhanced spatial information capture and object detection. Transformers, initially for NLP, have shown promise in computer vision tasks, with WIT achieving impressive results, especially with large datasets. Recently, studies extended transformers to object detection and video understanding, offering flexibility, scalability, and capturing spatial temporal information. Overall, advancements in deep learning, CNNs, and transformers have greatly improved hand gesture recognition and led to more effective systems in computer vision. Let's start the comparison with 2D CNNs. Our focus is on developing custom and straightforward 2D CNN architecture tailored specifically for real-time applications that may run on smartphones. The architecture includes two convolutional layers with filter sizes 11 by 11 and 5 by 5 for feature extraction, followed by two pooling layers with 2 by 2 kernels to downsample and aggregate feature efficiently. Next, a fully connected layer flattens the activation's values into a vectorized representation with 6,400 components, preparing the network for classification. Finally, a softmax layer normalizes output probabilities, enabling probabilistic interpretation and efficient inference of hand gestures. This streamlined architecture prioritizes computational efficiency and accuracy, making it suitable for real-time applications on smartphones. The alternative approach is visual transformer. ViT divides the input image into patches and adds positional encoding to capture spatial information. What sets ViTs apart is the inclusion of token embedding, often referred as a learned class token or classification token. This token represents global context of class information and is added to the sequence of patch embedding before being processed by the transformer encoder. The transformer encoder in ViT uses self-attention mechanisms to focus on image patches and token embedding, capturing long-range dependencies and extracting meaningful features pretty similar to CNNs. After processing through the transformer encoder, ViT generates output representations for each patch, but the most interesting presents a classification token, which is fed to MLP head to finally get probability predictions for each class, also similarly to CNN case. In this study, we utilized two datasets to evaluate the performance of our proposed models: the American Sign Language dataset and National University of Singapore dataset. The ASL dataset comprises 36 classes of hand gesture, including letters from A to Z and numbers from 0 to 9. This dataset consists of 2,515 samples with variations, each signed by 5 distinct performers. Performers demonstrated each symbol multiple times with varying frequencies. On the other hand, the NUS hand gesture dataset contains 2,000 images. This dataset involves 40 performers, each demonstrating gestures 5 times per class, resulting in total of 200 samples per class. Both datasets provide a diverse range of hand gestures and variations, allowing us to evaluate the robustness and accuracy of our proposed models across different scenarios. We use 3 key metrics to evaluate our model recall, precision, and F1 score. This metric recall measures the model's ability to correctly identify all instances of specific conjecture class among all instances of that class in the test dataset. Higher recall indicates better sensitivity. Precision shows the accuracy of the model in correctly identifying a specific conjecture class among all instances it predicted at that class. Higher precision signifies fewer false positives. The F1 score is a harmonic mean of recall and precision. It gives a balanced measure of model accuracy, considering both false positives and false negatives. For multi-class classification problem like ours, we calculate this metric independently for each class and then average them to get overall performance assessment. A higher F1 score indicates better overall model performance across all classes. The 2D CNN model showed superior performance on ASL dataset, achieving average F1 score of 0.88 across all characters. It attributes this attributed to the model's effectiveness in handling isolated symbols with less environmental influence. On the NUS dataset, the 2D CNN model achieved average F1 score of 0.87. In contrast, the ViT model initially yielded lower results in both datasets with F1 score of 0.84. However, additional training improves the ViT model performance, raising the average F1 score across all characters to 0.88. These findings demonstrate the strength of the 2D CNN models for isolated symbol recognition and potential for improvement in ViT models performance with extended training. Comparing CNN and visual transformer models reveals difference in size, memory usage, accuracy, and productivity. CNNs are compact, memory efficient, and effective in image tasks suitable for resource-limited setting. Visual transformers excel in capturing global dependency, but have a large size and higher memory needs. The choice depends on specifics, resources, trade-offs between complexity, accuracy, and efficiency. Moving forward, we aim to investigate specialized architecture for mobile devices, prioritizing efficiency without compromising accuracy. explore hybrid models combining 2D CNNs and visual transformers to reduce computational load while maximizing performance. Extend research to video-based gesture recognition using 3D CNNs or specialized visual transformers, enhancing temporal understanding and context awareness. These efforts will advance hand gesture recognition in real-world applications, ensuring efficiency, accuracy, and applicability across diverse platforms and scenarios.